Tonight, we are traveling back more than 300 million years to a moment when the sky itself operated under different limits. For a long stretch of Earth's history, the air carried far more oxygen than it does today, not as a sudden shift and not as a deliberate change, but as a slow side effect of forests spreading across low, waterlogged land. As plants grew and fell, their remains gathered instead of fading away, and carbon slipped quietly beneath the surface. As carbon left the atmosphere, oxygen rose. Fire became easier to start and harder to control. Decay slowed. Growth followed unfamiliar rules. Bodies that would feel fragile today encountered less resistance, and life expanded into the space it was allowed to occupy. In this world, insects were not small or fleeting. They moved through a sky without birds, above forests with almost no competition. Their size was not unusual within their own time, and it did not come from strength or aggression. It emerged from chemistry and physics briefly aligned. This balance lasted millions of years, long enough for ecosystems to settle into forms that now seem impossible. And when that balance shifted again, those forms vanished with it. But what changed the air enough to lift those limits on size? What conditions allowed insects to grow beyond what seems possible today? How did forests, decay, and chemistry reshape the rules of life itself? And why could this world never exist again? Tonight, we will drift slowly into that vanished sky, guided by evidence written into stone, ash, and air. But before we begin, if you enjoy videos like this, slow, soothing, and quietly filled with wonder, I'd love it if you gave this one a like and maybe tapped subscribe. It helps more curious minds like you find their way to this peaceful little corner of the internet. And if you'd be so kind, let me know in the comments, where are you winding down from tonight, and what time is it there? It's always a joy to see how far across the world this little sleepy corner of science travels. So now take a deep breath, let your shoulders loosen, and together let's step softly into a time when wings ruled the ancient sky. Long before the air grew unusually rich, the planet moved within narrower margins. Breathable gases circulated in proportions that imposed quiet restraint, not through violence or scarcity, but through balance. Oxygen remained present yet modest, diluted by higher levels of carbon dioxide and other gases released by volcanoes, shallow seas, and exposed rock. The sky carried weight differently then, not as an active force encouraging expansion, but as an invisible ceiling pressing gently downward on every living form that relied upon it. On land and in water, early animals navigated this atmosphere with bodies shaped by necessity rather than possibility. Insects, newly established on shorelines and forest edges, exchanged gases through thin tubes that depended on slow diffusion. Amphibians, bound to damp ground and water, absorbed oxygen through permeable skin and simple lungs that worked best when bodies stayed close to the surface. These systems were effective within limits, but they scaled poorly. As size increased, distance within the body grew faster than the ability of oxygen to reach every cell. Growth encountered resistance not from predators or climate, but from geometry itself. Physics enforced these boundaries with calm consistency. Diffusion works efficiently over short spans, but becomes unreliable across thicker tissues. Chemistry reinforced the same message. Lower oxygen concentrations reduce the gradient that drives gas exchange, slowing the movement of life's most essential molecule. Energy budgets tightened. Metabolism remained cautious. Bodies stayed compact, close to the environments that supplied what they needed. Wings, when present at all, were brief experiments rather than stable designs. The air did not invite long suspension. Amphibians reflected these constraints in their posture and movement. Most lingered where water softened the demands of gravity and breathing. Their growth traced the edges of ponds and marshes, not because they lacked potential, but because the planet's chemistry had not yet relaxed its grip. Even plants, though spreading steadily, recycled quickly. Fallen material decayed, returning carbon to the air and maintaining an atmospheric state that resisted dramatic change. Time itself became the slowest and most important factor. Shifts in atmospheric composition do not respond to seasons or lifetimes. They accumulate through countless small exchanges between rock, water, air, and living tissue. For oxygen to rise meaningfully, carbon must be removed persistently, not in bursts but across epochs. Before that removal began in earnest, the system held steady. Limits remained visible, yet unremarkable, shaping life without spectacle. In this earlier world, nothing strained against those boundaries. Evolution adjusted incrementally, refining efficiency rather than scale. Size was not a goal withheld, but a state not yet permitted. The air, the chemistry within it, and the slow pace of geological change work together to keep life proportioned, grounded, and contained, awaiting conditions that would later loosen the rules without ever announcing their arrival. The land itself began to linger. Near the equator, continents lay low and wide, their surfaces stretched flat beneath a sun that rarely varied in strength or angle. Rain arrived often and stayed longer than it left. Water gathered in broad, shallow basins and refused to drain away, spreading across floodplains and shallow seas that blurred the boundary between land and water. Over time, these saturated margins became permanent, forming vast wetlands that reshaped the face of the planet. Within this warm stillness, forests expanded without interruption. Tree-like plants rooted into soft ground and rose slowly above the waterlogged soil. Their growth did not cluster into isolated groves or retreat with dry seasons. Instead, vegetation spread outward in every direction, following the unbroken contours of the land. Rivers wandered lazily, changing course without cutting deeply, leaving behind new channels and drowned ground that quickly filled with green again. From horizon to horizon, the terrain repeated itself in gentle variations of trunks, fronds, and shallow pools. The climate offered little resistance. Temperatures remained mild and steady, shaped by shallow seas that stored heat and released it slowly. Frost rarely touched the surface. Storms arrived without sharp edges, their rain falling into landscapes already prepared to receive it. In this consistency, forests did not need to recover or adapt rapidly. They simply persisted, year after year, generation after generation, building layers of living structure atop soft foundations. Plant life dominated everything visible. There were no open meadows or flowering fields, no gaps cleared by grazing or browsing. Leaves, spore-bearing fronds, and towering stems crowded the air and filtered the light, turning daylight into a dim green glow beneath the canopy. The forest floor was less a surface than a volume, a suspended space of tangled growth, where stems crossed water and roots disappeared into unseen depths. Movement through this world followed the slow paths of water rather than solid ground. Across these regions, distance lost its meaning. Forests were not separated by mountains or deserts. They blended into one another across continents, uninterrupted by barriers that would later divide ecosystems. The planet's flatness allowed this continuity, letting plant-dominated environments extend farther than any woodland that would follow in later ages. From above, the land would have appeared textured and alive, a single connected system breathing gently under the sun. Nothing in this landscape resembled modern forests. There was no seasonal color, no fallen leaves crunching underfoot, no clearings shaped by fire or frost. Growth accumulated quietly and steadily, guided by warmth and water rather than competition or disturbance. These endless wet forests formed the stage on which the rest of the Carboniferous world would unfold, not as a backdrop of scenery, but as a living expanse that defined what land itself could become. Within the stillness of those ancient wetlands, plants began to change their internal architecture. Growth was no longer limited to soft tissues that bent and collapsed under their own weight. A new material spread quietly through stems and trunks, reinforcing them from the inside. This substance, lignin, did not announce itself in form or color, yet it altered what plants could become by allowing structure to endure. As lignin appeared, early trees gained rigidity. Trunks rose straighter and remained upright instead of sagging into the saturated ground. Height became stable rather than temporary. Branches could extend outward and hold their shape, lifting leaves and spore-bearing structures higher into the filtered light. Forests responded almost immediately, not by expanding faster, but by deepening vertically. Layers of growth stacked above one another, creating shaded interiors and thick canopies that slowed movement of air and water alike. These strengthened tissues changed the rhythm of the forest. Wind moved differently through lignin-supported trunks, slowed by resistance that did not exist before. Fallen plants no longer collapsed completely into the wet ground. They remained partially intact, forming dense tangles that spanned pools and channels. The forest floor became less defined, blurred beneath a network of fallen stems that did not easily surrender their form. The innovation carried a consequence that few organisms could answer. Lignin proved remarkably difficult to dismantle. The communities that thrived in these wetlands had evolved to process softer plant matter, breaking down simple tissues and returning them to circulation. Faced with this new material, decay faltered. Microbes and early decomposers passed over lignin-rich remains, unable to penetrate their structure efficiently. What fell did not disappear. It accumulated. Season by season, fallen wood layered upon itself. Branches sank into shallow water and stayed recognizable long after softer plants dissolved. Trunks lay embedded in mud, their interiors slowly darkening while their form persisted. The wetlands grew denser and heavier with their own history. Each generation of forest left behind a physical record that resisted erasure. This buildup altered the forest without movement or sound. Channels filled more easily. Water lingered longer around roots. Ground rose in some places, not through uplift, but through accumulation. The land became increasingly shaped by what plants left behind rather than what they actively supported. The forest was no longer just living growth, but preserved structure. Lignin did not spread with intention. It offered stability, and stability reshaped the environment around it. Trees reached higher, canopies thickened, and the interior of the forest became a place where light struggled to penetrate fully. Meanwhile, the quiet persistence of undecayed plant matter laid the groundwork for deeper transformation. Without dramatic change or visible disruption, the forests began storing themselves, layer upon layer, turning growth into lasting presence and setting the stage for consequences that would unfold long after the first reinforced trunks took root. The shift did not begin in the sky, but beneath still water and quiet ground. Across the endless wetlands, fallen plants slipped below the surface instead of remaining exposed to open air. Stems, trunks, and dense mats of vegetation settled into saturated soil where water pressed gently from all sides. In these places, movement slowed. What would once have been broken down and returned upward now sank and stayed. Within this submerged world, carbon followed an unfamiliar path. Instead of cycling quickly back into the atmosphere, it became locked into thick layers of plant remains. Oxygen poor conditions limited the activity of organisms that normally dismantled organic matter. Decomposition faltered, not completely, but enough to change the balance. Each season added another thin layer of preserved growth. Over long stretches of time, those layers thickened into something closer to sediment than soil. As this material accumulated, carbon gradually withdrew from circulation. It did not vanish abruptly or dramatically. Its departure unfolded quietly, molecule by molecule, as burial outpaced release. The atmosphere responded slowly, registering the absence as a subtle shift rather than a disruption. Carbon dioxide levels edged downward, not in steps, but as a long, shallow curve drawn across millions of years. This slow removal carried weight far beyond the wetlands themselves. Carbon dioxide, once abundant, became less dominant in the air above the forests and shallow seas. The planet adjusted without awareness or intention. Temperatures, winds, and rainfall patterns felt the change only faintly at first, yet the trend persisted. The sky began to hold a slightly different balance of gases, shaped not by a single force, but by the steady patience of burial. Below the surface, pressure increased. Layers compressed earlier growth, squeezing water away and locking carbon into increasingly stable forms. What began as fallen plant matter slowly transformed under heat and weight, becoming part of the planet's long-term memory. This process removed carbon from the short rhythms of life and placed it into spans of time measured in geological quiet. The consequences extended outward, touching systems far removed from the original forests. With less carbon dioxide returning to the air, the atmosphere shifted toward a new equilibrium. The change unfolded too slowly to be noticed by individual organisms, yet profoundly enough to alter the conditions under which life operated. The planet did not tip or lurch. It eased into a different state, guided by the cumulative effect of countless buried seasons. This was not a cycle completing itself, but one drifting out of balance. The return pathway for carbon had narrowed, while the pathway into storage remained wide and open. Over millions of years, that imbalance reshaped the atmosphere from below, driven by wetlands that quietly kept what once would have been released. In the deepening layers of preserved plant matter, the sky above began to change, not through sudden loss, but through long, deliberate absence. The atmosphere adjusted without ceremony. As carbon dioxide thinned, space opened within the air itself, not as emptiness, but as opportunity for another gas to accumulate. Oxygen, already present in modest amounts, began to occupy that space simply because fewer carbon atoms were returning to claim it. The balance shifted not through force or instability, but through slow arithmetic written into the exchange between air, water, and light. Photosynthesis continued its quiet work across vast stretches of green. Sunlight struck leaves and fronds, and energy flowed into chemical bonds that separated carbon from oxygen. With less carbon cycling back upward, the oxygen released by this process lingered longer than before. Each pulse was small, nearly invisible against the scale of the sky, yet persistent. Over time, the accumulation became measurable, not in moments, but across epochs. This was not a runaway reaction. Oxygen did not flood the atmosphere or surge upward in dramatic leaps. Chemical buffers moderated its rise. Reactions with exposed rock, dissolved minerals, and reduced compounds in soils and shallow seas absorbed much of what was produced. These sinks slowed the process. smoothing what might have been sharper change into a gradual incline. The planet resisted imbalance, allowing the shift only at a pace it could accommodate. Scientific reconstructions suggest that oxygen levels climbed far beyond modern proportions during this period. Estimates vary, but many converge on a range significantly higher than today's 21%, possibly reaching 30% or more at peak. These numbers do not imply precision, but direction. They reflect a sky that had become distinctly different in composition, even though its appearance remained unchanged to any observer standing beneath it. What mattered most was not the final percentage, but the rate. The rise unfolded over tens of millions of years, slow enough for chemical systems to adjust continuously. No sharp boundary marked its beginning or end. Instead, oxygen crept upward as carbon dioxide eased downward, their paths linked through countless small reactions rather than singular events. The atmosphere behaved less like a switch and more like a tide, advancing with patience and retreating only when conditions later demanded it. Heat, pressure, and circulation patterns adapted along the way. With changing gas proportions, the air carried energy differently, holding and releasing warmth in subtly altered ways. Yet nothing fractured or failed. The sky absorbed the transition as part of its ongoing conversation with the surface below. Stability emerged not from stillness, but from balance in motion. This quiet rise altered the chemical backdrop of the planet long before its consequences became visible. Oxygen accumulated because conditions allowed it to remain, not because it was driven to increase. Its presence grew steadily, almost cautiously, until the atmosphere crossed thresholds that would later reshape what was possible. At the time, the change remained diffuse and gentle, a slow brightening of the air that unfolded without sound, sign, or sudden shift. Breathing did not require lungs in this world, only proximity. Insects exchanged gases through a network of narrow tubes that opened along the body and branched inward, delivering oxygen directly to tissues. Air moved through these passages without pumping or circulation, guided instead by gradients that favored motion from higher concentration to lower. This method was simple, quiet, and reliable, provided distances remained short. Diffusion works best across thin spaces. In small bodies, oxygen reaches every cell quickly enough to meet demand. As size increases, that same process slows. Pathways lengthen, surfaces thicken, and the time required for molecules to travel inward begins to exceed what active tissues can tolerate. Muscles, nerves, and organs depend on rapid exchange. When diffusion cannot keep pace, growth encounters a physical ceiling set not by design, but by geometry. Under modern conditions, this limit arrives early. With lower concentrations of oxygen in the surrounding air, the gradient driving diffusion is modest. Oxygen enters the body more slowly and spreads less efficiently. Larger insects would experience shortages deep within their tissues, where movement and metabolism demand consistent supply. The physics of gas movement narrows what forms can persist, favoring compact frames and thin profiles. When oxygen concentrations rise, the same structures behave differently. A steeper gradient allows more oxygen to enter with each breathless exchange. Molecules travel faster and penetrate farther before their momentum fades. The internal distances that once imposed constraint become less restrictive, not because anatomy changes, but because the environment supports greater throughput. Diffusion gains reach without gaining speed. In such conditions, insects did not need to reinvent themselves. Their tracheal systems already existed, refined over long spans of evolutionary time. With more oxygen available outside the body, these networks suddenly supported volumes of tissue that would later become impossible. Muscle fibers thickened, wings grew broader, bodies extended along forms already established, expanding into dimensions previously closed to them. The physics remained the same. Diffusion did not transform into circulation, nor did insects develop lungs or pumps. What changed was the margin for error. Higher oxygen allowed inefficiencies that would otherwise prove fatal. It softened the penalties of scale, permitting growth without structural innovation. Size emerged not as a breakthrough, but as a continuation. These principles apply quietly and universally. They do not favor ambition or adaptation, only balance. When environmental conditions align, existing systems express their full range. When those conditions narrow, the same systems retreat. Insects of this era occupied a window where mechanics briefly allowed greater reach, holding open a door that would later close. This expansion did not push against physical law. It followed it precisely. Breathing without lungs remained bound by diffusion, just temporarily liberated by circumstance. As long as the air sustained that gradient, larger bodies functioned smoothly, their internal distances finally matched by the chemistry around them. The moment that balance shifted, the ceiling returned, and the quiet mathematics of diffusion resumed its familiar limits. Above the forests, space existed without claim. The air stretched outward not as territory guarded or contested, but as volume left largely untouched. Nothing larger than an insect regularly occupied it. No feathers cut through the light. No leathery wings traced long shadows across the canopy. The sky was present, open, and waiting. At this stage in Earth's history, flight had not yet diversified. Vertebrates remained bound to land and water, their movements shaped by gravity and surface. The sky was not part of their daily passage. What drifted upward from the forests encountered little resistance, meeting currents and warmth rather than pursuit. This absence shaped the vertical dimension of the world as clearly as climate shaped the ground below. For insects, this openness offered more than room. It provided safety. Movement above the canopy carried fewer risks than movement across it. On the forest floor, paths were crowded and visibility was low. Beneath dense vegetation, ambush and accident were constant companions. Above the leaves, the air was clearer, steadier, and free from many of the dangers that governed life below. Rising was not a conquest, but an extension of stability. Insects expanded upward because nothing pushed back. Their wings already allowed short flights between stems and pools. With space unoccupied, those movements grew longer and higher. Air currents became pathways rather than obstacles. The canopy transformed into a launch point, not a ceiling. Each increase in height reduced encounters with ground-based threats and opened access to sunlight-filtered layers of the forest unavailable to crawling forms. The absence of aerial predators mattered deeply. No eyes scanned the sky for movement. No bodies specialized in pursuit or interception. Flight carried energy costs, but few penalties. Speed did not need to be extreme. Maneuverability did not require refinement against opposition. Even large bodies could remain aloft without inviting immediate danger. The sky allowed inefficiency, granting time and margin to those who used it. As insects rose higher, the vertical structure of the ecosystem adjusted quietly around them. The upper air became part of daily circulation, not an occasional crossing. Movement occurred above branches rather than through them. This upward drift was gradual, guided by opportunity rather than pressure. The sky filled because it could, not because competition demanded it. This openness endured for millions of years. It persisted not through balance between rivals, but through absence. When no group occupies a space, the first to enter often defines its use. Insects did so without opposition, shaping the earliest aerial pathways through repetition alone. Their presence did not exclude others, only preceded them. The sky of this time belonged neither to dominance nor conflict. It remained a quiet extension of the forest, a place where motion unfolded without pursuit. In this calm emptiness, flight became ordinary, height became accessible, and the air itself became part of the landscape. Size became visible in the air long before it became dramatic in the fossil record. Over wetlands and open water, insects emerged whose proportions exceeded anything familiar today. Their wings did not flicker like brief gestures. They extended outward with presence, carrying bodies that moved steadily rather than darting. In the stillness above ancient forests, these forms pass slowly across light, leaving impressions not of speed or threat, but of scale. Some of the largest known flying insects reached wingspans comparable to modern birds, where today a large dragonfly fits easily within a hand's breadth. These earlier relatives stretched across lengths measured in feet. Their bodies remained narrow, supported by wings that balanced lift with control. Compared to present-day insects, the difference was not merely size, but rhythm. Movement favored gliding arcs and sustained travel rather than abrupt turns. Fossils preserve these proportions with surprising clarity. Compressed into fine sediment, wings leave behind dense networks of veins that outline structure and strength. These patterns reveal surfaces built to distribute weight efficiently across wide spans. The spacing of veins suggests wings designed for endurance rather than rapid acceleration. Broad surfaces caught air gently, allowing lift to build without constant exertion. In preserved impressions, the wings curve subtly, shaped for stability in warm, rising air. The bodies attached to these wings tell a similar story. They are streamlined and elongated, not reinforced for impact or struggle. Legs lack the heavy spines seen in later predatory insects. Mouth parts, where preserved, appear suited for modest feeding rather than violent capture. Everything about their form suggests an animal adapted to movement through open space, not confrontation within it. Flight style likely followed the same principles. Rather than sudden bursts of pursuit, these insects probably relied on steady motion, riding thermals, and gentle currents above the landscape. The air of the time supported extended flight with fewer penalties, allowing bodies of this scale to remain aloft without constant effort. Energy was conserved through glide and drift, not spent in repeated struggle. Their size did not signal dominance through aggression. No evidence suggests they functioned as aerial hunters in the modern sense. Without birds or other flying vertebrates, there was little pressure to refine speed or attack behaviors. The sky did not demand violence, it offered space. These insects occupied it by existing within its allowances, not by contesting it. In the fossil record, this becomes clear. There are no signs of reinforced jaws or grasping limbs built for combat in the air. Instead, there is consistency. Large wings, light bodies, and structures suited to endurance repeat across specimens separated by time and location. The giants of the Carboniferous era were not anomalies or terrors. They were expressions of an environment that briefly permitted flight to grow calm, expansive, and immense, leaving behind traces of a sky that once held more than it does now. Below the flight paths and drifting wings, the forest lived in layers. Light thinned as it passed through overlapping leaves and broad fronds, settling into a muted glow near the ground. Water pooled everywhere, collecting along roots, fallen stems, and shallow channels that never fully dried. This shaded world moved slowly, shaped less by seasons than by saturation. Giant insects were present here, not as rulers, but as participants. When they descended from the air, they folded into the same networks that supported smaller forms. Their size did not separate them from the system beneath the canopy, it linked them to it. Larval stages unfolded in water or damp soil. Adults rested among trunks and leaf clusters, returning nutrients downward through waste and decay. What passed overhead eventually became part of what remained below. Amphibians found this environment especially accommodating, with skin that relied on moisture and bodies that moved comfortably between land and water. They thrived in the constant wetness. Pools served as nurseries. Muddy banks offered shelter. Shallow channels connected habitats without interruption. Growth proceeded steadily, supported by abundant food and reliable conditions. These animals did not need to travel far. Everything they required lay close at hand. Arthropods dominated the forest floor. Millipedes, early insects, and other jointed forms moved through layers of fallen plant matter that softened each step. Decomposition was slow, but life still fed from the surface inward. Smaller creatures processed what larger ones could not. Fragmented plant material passed through countless mouths, inching downward toward burial. The ground itself became animated, shifting subtly as bodies moved through it. Connections between land, air, and water remained stable. Nothing functioned in isolation. Rain carried material from canopy to soil. Floods lifted nutrients back into circulation. Wings moved spores and fragments between spaces that crawling alone could not connect. Each layer supported the others by sharing movement rather than competing for dominance. This stability allowed complexity without fragility. The absence of sharp boundaries between habitats reduced stress on organisms moving between them. A fallen tree did not end life beneath it, it created more surface. A flooded channel did not displace communities, it extended them. Even large insects fit into this rhythm, their scale absorbed by systems already accustomed to density and overlap. Life beneath the canopy persisted through continuity rather than change. Interactions repeated themselves with slight variation, enough to sustain diversity without disruption. The ecosystem held together through flow, not balance enforced by control. In this submerged and shaded world, air met leaf, leaf met water, and water met soil without interruption, forming a living fabric that supported everything above it and quietly defined what endurance looked like in a forest that never truly slept. Flame moved through this world with unfamiliar ease. A spark that might have faded in another age could persist here, carried by air that fed combustion readily. Fire did not wait for rare alignments of dryness or wind. It traveled through forests already heavy with growth, finding pathways among fallen branches, dense litter, and standing trunks that rose from saturated ground. Evidence of burning appears across the record of this time, preserved as charcoal fragments embedded in ancient sediments. These traces recur again and again, spread across continents rather than confined to isolated events. They speak of fires that ignited often, sometimes creeping slowly through understory, sometimes climbing upward along trunks into the canopy. The landscape carried memory of flame without carrying signs of collapse. In an atmosphere rich enough to support combustion more easily, fire behaved less like an intruder and more like a process. Flames moved at lower temperatures and with steadier persistence, consuming surface material while leaving deeper layers intact. Wet ground limited how far heat could penetrate, keeping roots protected even as leaves and fallen wood burned away. The result was renewal without devastation. Ecosystems adjusted to this rhythm gradually and without intent. Plant communities tolerated frequent burning by growing quickly and regenerating from protected tissues. New shoots emerged from bases and buried structures that fire could not reach. Ash returned nutrients to the surface, enriching soil already thick with organic material. Over time, burning became part of the landscape's circulation rather than a force that interrupted it. Fire also shaped structure. By clearing accumulated debris, it prevented forests from choking under their own weight. Channels reopened where fallen material had once blocked water. Light reached lower layers after flames passed, encouraging new growth beneath the canopy. This balance allowed forests to persist without stagnation, renewing themselves without loss of continuity. For animals, frequent fire altered movement rather than survival. Amphibians retreated into water and damp ground where flames could not follow. Arthropods sheltered beneath debris or within soil, emerging as conditions settled. Larger insects navigated above burning areas, their mobility allowing them to avoid heat while continuing to move between habitats. Life adapted by shifting position, not by resisting the process. Fire's role remained regulatory. It recycled surface growth, returned nutrients, and maintained openness within otherwise dense systems. It did not signal the end of forests, nor did it erase complexity. Instead, it reinforced patterns that allowed stability to persist across time. Burned areas did not remain barren. They re-entered the cycle almost immediately, folding back into the broader ecosystem. In this world, flame belonged to the landscape as surely as water and plant life did. It acted without intention or excess, guided by conditions that supported its presence. High oxygen allowed fire to exist more freely, yet the surrounding environment shaped its reach and restraint. The result was a planet where burning marked renewal rather than ruin, and where heat moved through living systems as a quiet partner in their long endurance. Oxygen is often treated as a gift without consequence, yet within living tissue it carries a double nature. It supports the chemistry that releases energy, allowing cells to function, repair, and grow. At the same time, it participates in reactions that can damage those same cells if not carefully managed. Life has always existed within this tension, relying on oxygen while guarding against its excess. At higher concentrations, oxygen increases the likelihood of reactive byproducts forming inside cells. These molecules interact readily with membranes, proteins, and genetic material. Left unchecked, they alter structure and function at the smallest scales. Cells respond by investing energy into protective systems, enzymes, and barriers that limit harm and repair damage as it occurs. This constant maintenance becomes part of daily survival, invisible but demanding. The cost of this protection grows as oxygen availability increases. More oxygen means more opportunities for damaging reactions, and therefore more resources devoted to control rather than growth or reproduction. Tissues operate closer to their tolerance limits. Small disruptions that would otherwise be absorbed can propagate further, affecting systems that depend on long-term stability. Life continues, but with less room for error. Different organisms experience this strain in different ways. Simpler bodies with fewer layers and shorter lifespans can tolerate narrower margins. persisting even when cellular stress increases. More complex systems accumulate damage over time, especially when repair cannot fully keep pace. Vulnerability does not arrive suddenly. It builds quietly as balance becomes harder to maintain across years and generations. This narrow window defines what can endure. Oxygen supports active metabolism, but only within bounds that biological defenses can manage. Above those bounds, even abundance becomes a pressure. Cells work harder to remain intact. Development tightens its tolerances. Reproduction depends on precise timing and conditions. Stability becomes conditional rather than assured. These constraints do not imply fragility in the moment. Life can flourish under high oxygen while conditions remain steady. Growth proceeds. Ecosystems persist. Yet the underlying biology carries a load that cannot be ignored indefinitely. Systems operating near their limits are less resilient to change, more sensitive to shifts in temperature, nutrition, or chemistry. What sustains them also exposes them. This is how abundance creates vulnerability. Oxygen enables scale and activity, but it also demands control. The balance between benefit and harm grows sharper as concentrations increase. Biological systems compensate as long as they can, adjusting pathways and tolerances without awareness or intention. Over long spans of time, however, even slight imbalances matter. Within cells, molecules continue their quiet interactions, supporting life while testing its boundaries. Oxygen remains essential, yet never neutral. Its presence defines both capability and cost, shaping which forms persist comfortably and which exist at the edge of their biological capacity. In this way, life under oxygen-rich conditions carries hidden strain, sustained not by excess alone, but by the continual effort to survive within it. Size in this world did not announce threat. It carried presence rather than menace, a quiet mass moving through air that offered little resistance. Large insects did not dominate through force or intimidation. Their scale reflected conditions that allowed bodies to expand without penalty. Within the forests and skies of this time, being large meant fitting comfortably into what the environment permitted, not overwhelming it. Greater size offered practical advantages that had nothing to do with aggression. Larger bodies changed how heat moved through tissue, slowing the rate at which warmth was lost to surrounding air. In a landscape defined by steady temperatures and saturated ground, retaining heat supported consistent activity without the need for rapid movement. This stability favored endurance over bursts of speed, allowing insects to remain active longer with less variation in effort. Flight benefited from this balance. Broad wings supporting heavier bodies moved more air with each stroke, generating lift efficiently at lower frequencies. Instead of rapid beating, motion settled into slower, measured rhythms. Energy expenditure dropped as lift became easier to maintain. Air currents and gentle thermals carried mass with little additional cost. Flying became a matter of staying aloft rather than constantly fighting gravity. This efficiency shaped behavior. Large insects did not need to chase or evade frequently. Their movement was deliberate, guided by access rather than pursuit. Slow flight reduced the energy required to navigate wide areas, linking distant patches of forest and water without urgency. Size allowed them to travel farther while spending less, an advantage rooted in physics rather than dominance. On the ground, scale offered similar benefits. Larger bodies crossed soft terrain with stability, distributing weight across longer limbs and broader contact points. Movement remained steady Even through tangled plant matter and shallow pools, size reduced vulnerability to minor obstacles rather than increasing danger to others. These insects were not built for confrontation. They were built for persistence. Modern perspectives often reinterpret size through fear. Contemporary ecosystems associate large flying forms with predation and threat, shaped by birds, bats, and human experience. That lens does not fit this earlier world. There were no aerial rivals demanding speed or aggression. The sky did not punish calm movement, it rewarded efficiency. Fossil evidence supports this view through absence as much as presence. Structures associated with violence, such as reinforced jaws or grasping appendages designed for struggle, remain rare or understated. Instead, preserved forms emphasize wings, balance, and support. Size extended existing designs rather than transforming them into weapons. These insects occupied their environment without tension. Their scale worked with the conditions around them, regulating temperature, conserving energy, and enabling travel across an open sky. Fear arrives later, projected backward from worlds shaped by conflict and competition. In the Carboniferous era, size simply meant that life had room to be larger, and that room was used quietly, without spectacle or threat. Change arrived without drama. The forests remained, the air stayed rich, and the rhythms of daily life continued much as they had for millions of years. Yet beneath that continuity, small adjustments began to register across the planet. Patterns that once repeated with near perfect regularity started to drift. Rainfall varied slightly from one long interval to the next. Temperatures held steady, but not with the same quiet consistency. The world was not breaking, but it was no longer resting fully at ease. Far to the south, beyond the dense equatorial wetlands, conditions shifted more noticeably. Vast landmasses near the pole began to cool as long-term processes altered how heat moved around the planet. Snow that once melted away began to persist. Ice gathered slowly, not in sudden advances, but as seasonal traces that returned more reliably each cycle. Over time, these accumulations thickened, pressing outward across high southern regions. This glaciation did not announce itself to the forests near the equator. Ice and swamp coexisted at opposite ends of the world, connected through currents of air and water rather than proximity. As ice expanded, global temperatures edged downward by small increments. The change was subtle, yet persistent, carried forward by the same processes that had quietly reshaped the atmosphere earlier. Carbon removal, once a driver of abundance, now extended its influence into climate itself. With less carbon dioxide circulating freely, the planet retained heat differently. Oceans absorbed and redistributed energy along altered gradients. Winds shifted in strength and pattern. Seasonal contrasts grew slightly sharper. None of these changes were sudden enough to disrupt ecosystems outright. They accumulated slowly, expressed not as catastrophe, but as pressure building beneath the surface of stability. The Carboniferous system had been shaped by balance between growth, burial, and renewal. As that balance leaned further in one direction, strain followed. Wetlands remained extensive, yet their margins became less predictable. Some regions experienced longer periods of saturation, while others began to dry more consistently. Forests responded by fragmenting at their edges, even as their cores remained intact. This growing tension did not immediately reduce diversity or size. Life continued to function within familiar bounds. Yet the conditions that supported such generosity became narrower. Stability depended on maintaining precise relationships between land, air, and water. As global cooling progressed and ice claimed more southern ground, those relationships grew harder to sustain everywhere at once. The system had not reached a breaking point, but it had begun to resist itself. Processes that once reinforced one another now pushed in competing directions. Long term carbon burial continued to cool the planet, while ecosystems built for warmth and saturation struggled to adjust at their edges. The world entered a phase where its internal feedbacks no longer aligned perfectly. These early signals did not erase what had come before. They layered themselves atop an existing world, quietly altering its tolerance for change. The Carboniferous remained intact, yet its foundations tightened. What had once felt endlessly permissive became slightly constrained. The strain was faint, almost imperceptible in any single moment, but across deep time, it marked the beginning of a slow departure from balance. The surface of the planet never stays fixed, even when change feels slow. Over long spans of time, continents continued their gradual movement, shifting position by distances too small to notice in a lifetime, yet large enough to reshape climate. As land drifted, pathways for moisture altered. Winds no longer followed the same routes. Rain that once fell reliably across wide regions began to favor some areas while bypassing others. These changes reached the wetlands first at their margins. Places that had remained saturated for millions of years began to experience longer dry intervals. Water lingered less persistently in shallow basins. Channels that once overflowed year round narrowed during extended stretches. The shift did not erase wetlands outright, but it weakened their continuity. Permanence gave way to variation. As rainfall patterns grew uneven, forests responded by separating. Dense plant systems that had stretched uninterrupted across flat land now encountered breaks. Some stands remained lush, anchored to reliable water. Others thinned where soil dried more often. The once continuous green expanse began to resolve into patches, connected by corridors rather than endless cover. Boundaries appeared where none had existed before. This fragmentation changed the internal balance of the forest. Edges expanded. Light penetrated differently. Air circulated more freely through gaps that had previously been shaded and still. These alterations affected growth rates and composition, favoring plants better suited to variability over those dependent on constant saturation. The structure of the landscape grew more complex, but less forgiving. Ecosystems shaped by generous atmospheric conditions began to feel strain. Organisms adapted to stable, oxygen rich environments depended on consistency as much as abundance. As forests broke apart, local conditions fluctuated more sharply. Temperature and humidity varied across short distances. The margin for maintaining internal balance narrowed, especially for larger forms that relied on predictable surroundings. Movement became more costly. Large insects that once crossed uniform terrain now encountered open stretches where shelter and moisture were less certain. Amphibians faced longer distances between reliable pools. Arthropods that thrived in thick litter found fewer uninterrupted layers to inhabit. These pressures did not eliminate life, but they forced adjustments that favored smaller bodies and more flexible habits. The atmosphere remained supportive, yet the ground below no longer matched it everywhere. Oxygen-dependent systems functioned best where forests stayed intact. In fragmented regions, their advantage diminished. The relationship between air and landscape, once aligned across broad areas, became uneven. Stability retreated into pockets rather than spanning continents. This stage marked a turning point not defined by collapse, but by separation. The Carboniferous world did not vanish, yet it lost its cohesion. Continental movement introduced variation faster than ecosystems built for uniformity could fully accommodate. What had once been an uninterrupted environment became a mosaic, still rich, still active, but increasingly divided. Fragmentation introduced limits that abundance alone could not overcome. As land shifted and water followed new paths, the world tightened its tolerances. The immense systems that had flourished under uniform conditions now operated within narrower spaces, carrying forward their momentum while adapting to a planet that was slowly, quietly, becoming less accommodating. The change began quietly within the forest floor. For millions of years, dense plant matter had accumulated faster than it could be processed, forming thick layers that resisted decay. Over time, new organisms emerged that could interact with this stored material in ways previously unavailable. Their presence did not transform the forest overnight, but it introduced a subtle reversal in long standing patterns. These organisms possessed the ability to break down lignin, the structural material that had once protected fallen wood from rapid decomposition. With access to this tough tissue, plant remains no longer lingered unchanged within waterlogged ground. Decay resumed its work more completely, reducing long preserved structures into smaller components that could move again through soil and water. What had been locked away gradually returned to biological circulation. As decomposition progressed, carbon followed new pathways. Instead of remaining buried under layers of sediment and pressure, it began re entering the system through respiration and chemical exchange. Carbon dioxide was released back into the atmosphere from processes that had long been muted. This release did not surge or spike. It accumulated slowly, restoring balance between storage and return that had been absent for much of the period. With carbon cycling more efficiently, the conditions that had supported exceptionally high oxygen became narrower. The atmosphere responded not with collapse, but with adjustment. Oxygen production continued, yet its accumulation slowed as opposing processes strengthened. Chemical reactions that once favored retention now redistributed gases more evenly. The sky began to feel tighter, not heavier, but less permissive. This tightening reflected a shift in equilibrium rather than a loss of function. The atmosphere maintained its capacity to support life, but the margins that had once allowed extraordinary scale began to close. Systems adapted to abundance now encountered increasing constraint. The same air that had enabled generous diffusion and easy combustion grew incrementally less expansive in its allowances. Nothing about this transition was abrupt. It unfolded across vast spans of time, integrated into daily processes too small to observe individually. Forests continued to grow. Fire still moved across landscapes. Life persisted without sign of crisis. Yet beneath that continuity, the balance between burial and release had changed direction. Carbon no longer favored disappearance. It moved again, tracing loops rather than sinking into deep storage. As atmospheric composition shifted, stability narrowed. Oxygen-dependent systems remained functional, but their cushion of excess thinned. Reactions proceeded closer to their minimum requirements. The sky did not reject life, yet it no longer offered the same freedom of scale. Biological systems found themselves operating within stricter limits defined by chemistry rather than opportunity. This phase marked the end of an unusual openness. Oxygen did not vanish, but its peak had passed. The processes that once sustained extraordinary accumulation now balanced against forces that restored circulation. The planet continued its long conversation between land, air, and life, adjusting conditions without intent or urgency. In this tightening atmosphere, the Carboniferous world carried forward its momentum, unaware that the margins sustaining its giants were slowly closing. The sky did not close abruptly. Its change registered first through effort. Flight demanded slightly more from bodies that had once moved with ease. Lift still formed beneath wings, yet it required greater precision and steadier motion. Air that once carried mass generously now offered less support, turning the act of remaining aloft into a task that consumed more energy than before. As oxygen availability declined, diffusion within insect bodies delivered less margin. Muscles responsible for flight fatigued sooner. Recovery took longer. Wings that had once balanced size and efficiency now faced higher costs. Broad surfaces generated lift, but they also demanded sustained power to move through denser resistance. The same structures that supported calm, slow flight became liabilities when internal supply tightened. Large wings, once advantageous, grew increasingly expensive. Each stroke consumed more energy relative to what the body could comfortably provide. Long spans amplified drag during motion and required careful control to avoid loss of stability. In still air, maintaining altitude demanded continuous adjustment rather than relaxed gliding. The sky no longer rewarded scale alone, it favored restraint. Smaller bodies responded differently. Shorter internal distances allowed oxygen to reach tissues more reliably. Muscles recovered faster. Wings could beat more frequently without overwhelming metabolic limits. Compact forms tolerated variation in conditions with greater flexibility. Where larger insects strained to sustain flight, smaller ones remained efficient and responsive. These differences did not remove large insects immediately. Instead, they shifted probabilities. Individuals with slightly reduced size flew longer and fed more consistently. Those with marginally smaller wings maneuvered with greater control. Over generations, these advantages accumulated quietly. Size decreased not through sudden selection, but through gradual preference embedded in survival and reproduction. The process unfolded across long spans of time. Each generation carried forms close to those before it, differing by increments too small to notice in isolation. Yet over thousands of generations, the trend became clear. Wings shortened, bodies narrowed, mass retreated toward dimensions that balanced lift, energy use, and internal supply more effectively within the changing sky. This shrinking was not uniform. Different lineages adjusted at different rates, depending on habitat and behavior. Some maintained moderate size by limiting flight duration or remaining closer to the canopy. Others adopted more frequent flapping with reduced span. The common outcome remained consistent. Smaller bodies endured with greater ease. Nothing about this shift suggested failure. It reflected adaptation to mechanical reality. The physics of flight and diffusion imposed constraints that favored efficiency over scale. The sky had not rejected insects. It had refined the terms under which flight remained viable. Over time, the air grew less forgiving of excess. The immense openness that once allowed large forms to drift calmly began to favor forms that asked less of their environment. Flight persisted, but it changed character. What remained was not the disappearance of motion, but its refinement, shaped by a sky that slowly, steadily, required less mass to move through it. Reproduction slowly loosened its dependence on standing water. A fundamental shift unfolded within eggs themselves, as protective membranes formed layers that could regulate moisture, gas exchange, and nourishment internally. These amniotic eggs carried their own small environments, sealed enough to resist drying while remaining open to the surrounding air. Life gained the ability to begin away from pools and saturated ground without sacrificing development. This innovation altered where birth could occur. Eggs no longer required constant contact with water to survive. They could be laid in sheltered soil, beneath leaf litter, or within shallow depressions that held no permanent moisture. Development continued steadily inside these enclosed spaces, protected from fluctuation. Reproduction stepped beyond the wet margins that had previously constrained it. As this change spread, animals capable of producing amniotic eggs extended their presence into drier regions. Early reptiles moved outward from the wetlands into landscapes where evaporation exceeded saturation. Their bodies supported thicker skin that reduced water loss, and their movements no longer traced the outlines of pools and channels. They crossed ground that amphibians avoided, carrying life cycles that remained intact regardless of proximity to water. Dry interiors of continents, once sparsely occupied, began to support consistent animal presence. These areas offered fewer dense plants and less constant shade, yet they provided stability of a different kind. Seasonal variation existed, but it unfolded predictably. Reptiles adapted to these rhythms, using shelter and behavior rather than constant moisture to regulate their bodies. With this expansion came new forms of interaction. Insects encountered competitors that did not depend on wetlands or shallow water to persist. Reptiles fed on arthropods, disrupted breeding grounds, and altered movement patterns across fragmented landscapes. Pressure emerged gradually, expressed through overlap rather than confrontation. The sky and ground began to share influence, with species less restricted by humidity and water access. This competition did not overwhelm existing ecosystems. It redistributed advantage. Where once moisture defined opportunity, flexibility now mattered more. Insects that relied on wet environments retained strength there, but lost exclusivity beyond them. Amphibians persisted where water remained dependable, while reptiles claimed spaces previously underused. The boundaries between habitats sharpened as life diversified its strategies. The rise of land-based reproduction reshaped ecological balance without urgency or collapse. Life did not abandon water, it incorporated alternatives. Systems built entirely around saturation adjusted to coexist alongside those no longer bound to it. Movement across the landscape increased, linking regions that had once functioned separately. This shift marked a quiet widening of biological possibility. By freeing reproduction from constant water dependency, the planet invited new forms into spaces that had remained marginal. Competition expanded not through aggression, but through presence. The Carboniferous world grew more layered, not only vertically through canopy and air, but horizontally across drier ground. Life began to fill spaces that moisture had once guarded, carrying forward changes that would continue shaping ecosystems long after the great forests began to thin. The sky gradually filled with intent. What had once functioned as open volume became shared space, shaped by increasing movement and attention. Flight was no longer an act performed in relative isolation. Paths crossed more frequently. Air carried more signals, more interruptions, more urgency. The aerial world shifted from openness to interaction. New predators entered the air, bringing with them strategies refined through pursuit. Flight gained direction and speed. Movement above the canopy began to include interception rather than passage. Insects that had relied on steady motion now encountered trajectories that cut across their own. The sky learned complexity, not through sudden invasion, but through accumulation of competing ways to move. With this change came selective pressure that favored precision over presence. Large bodies, once tolerated by openness, became easier to track and anticipate. Broad wings that moved slowly through air offered little defense against focused pursuit. Success depended less on endurance and more on responsiveness. Smaller forms adjusted more easily, altering direction quickly and recovering from exertion with less cost. As aerial competition intensified, insects responded by narrowing their roles. Rather than occupying wide vertical ranges, many specialized into specific layers of the environment. Some remained close to the canopy, using cover as protection. Others limited flight to brief transitions, reducing exposure. Wings adapted toward maneuverability rather than lift alone. Bodies followed suit, shrinking gradually to match new demands. This specialization brought efficiency, but it also reduced dominance. Insects no longer defined the aerial world on their own. They shared it with animals built for speed, vision, and interception. The sky became a place of negotiation rather than extension. Survival favored subtlety rather than scale, timing rather than presence. Over generations, the effects compounded. Lineages that once supported large size shifted toward forms that balanced reproduction, evasion, and energy use more tightly. The immense wings of earlier eras left no descendants at that scale. Their advantages belonged to a world that no longer existed. What remained were refined descendants, carrying echoes of former abundance in structure but not in proportion. The loss of aerial dominance did not mark failure, it marked transition. Insects adapted by becoming diverse rather than immense. They filled niches shaped by competition, using specialization to persist where general presence once sufficed. The sky retained flight, but not generosity. It demanded efficiency, awareness, and restraint. This closing of openness reshaped ecosystems without erasure. Life redistributed itself across layers that now carried meaning and consequence. The air no longer belonged to a single group by default. It reflected a balance forged through interaction, where dominance gave way to coexistence. What ended was not flight itself, but a condition that allowed flight to expand without resistance. The Carboniferous sky had offered room without reply. The later sky answered back. In that answer, scale receded, and the aerial world settled into a more crowded, contested form, one shaped not by abundance alone, but by the presence of many ways to survive within the same moving space. The conditions that once permitted immense insects no longer align in the modern world. Oxygen remains abundant enough to support active life, yet it no longer reaches the concentrations that relaxed physical limits on diffusion. Within today's atmosphere, gases move efficiently only across short internal distances. Large bodies encounter constraints quickly, not because flight is impossible, but because sustaining it demands more than diffusion can reliably supply. The sky allows motion, but not excess. This mechanical boundary alone would be limiting, yet it is not acting in isolation. Modern ecosystems are densely occupied. The air is shared by birds, bats, and other flyers that specialize in pursuit, navigation, and sustained activity. These animals bring speed, vision, and coordinated movement into aerial space. Any large insect attempting to re-enter this environment would face competition refined through millions of years of conflict and response. Size would offer no refuge, only visibility. Fire behaves differently as well. Present-day regimes are shaped by lower oxygen and altered plant communities. Flames still move through landscapes, but they do so less frequently and with less persistence than in the Carboniferous. Fires are often patchy, episodic, and strongly influenced by seasonal dryness rather than continuous saturation. This pattern limits the accumulation and rapid recycling that once sustained extensive wet forests. Without those landscapes, the feedbacks that supported unusual atmospheric balance cannot reassemble. Forests themselves are no longer vast, uninterrupted systems dominated by simple plant forms. They are complex, layered, and often fragmented by climate, geography, and human influence. Decomposition proceeds efficiently. Carbon returns to circulation quickly. The long term burial that once shifted atmospheric chemistry remains possible, but it unfolds within a different context, moderated by diverse organisms that prevent prolonged imbalance. Evolution works within present constraints, not toward past outcomes. It does not store memory of former conditions or aim to restore them. Traits emerge when they are supported by environment and competition, not when they resemble historical success. For giant insects to return, multiple systems would need to realign at once: atmospheric composition, plant structure, fire behavior, and ecological vacancy. Each of these factors has followed a separate path since the Carboniferous, diverging steadily rather than looping back. Even if one condition shifted temporarily, the others would resist. Higher oxygen without extensive wetlands would increase biological stress without restoring mechanical freedom. Reduced competition without altered diffusion limits would still restrict size. The past arrangement depended on coincidence as much as causation, a rare overlap of processes unfolding together over immense time. The disappearance of giant insects was not an error corrected by smaller forms. It was a response to narrowing opportunity. Their absence today reflects stability rather than loss. The modern world is balanced differently, shaped by constraints that favor diversity and specialization over scale. What once filled the sky did so because the planet briefly made room for it. That room has since been repurposed. The Carboniferous giants belong to a specific alignment of physics and ecology. With those alignments gone, evolution continues forward rather than backward, carrying flight onward in refined, compact forms suited to a world that has learned to be less permissive and more crowded than it once was. Stone remembers chemistry more faithfully than motion. When insects fell from the air and settled into mud, ash, or fine sediment, their bodies entered conditions that slowed loss and preserved outline. What endured was not color or sound or behavior, but form shaped by material limits. Fossils became records of what chemistry allowed at the time, captured as impressions pressed into layers that hardened quietly around them. Insect fossils rarely preserve full bodies with depth intact. Instead, they hold surfaces, especially those built thin and wide. Wings fossilize well because of their structure. Dense networks of veins reinforce broad membranes, creating patterns that resist collapse long enough to be recorded. When sediment settles over a fallen wing, it presses into every ridge and channel, tracing its shape with remarkable precision. The result is an imprint that reveals size, proportion, and load-bearing design without preserving the tissue itself. These wings carry more information than simple outline. Vein thickness, spacing, and orientation indicate how forces once traveled across the surface. They show where strength was concentrated and where flexibility remained. From these details, scientists infer flight style, speed, and endurance, not by speculation, but by comparing physical constraints shared across living flyers. The wing becomes a diagram of mechanical possibility, frozen at the moment conditions supported it. Other parts of the insect record are less generous. Soft tissues decay quickly, leaving little trace. Muscles, organs, and sensory structures vanish unless sealed under rare conditions. What remains are fragments, outlines, and indirect signals. Fossils preserve what resisted loss longest, not what defined daily experience most completely. This imbalance shapes interpretation, offering clarity in structure while withholding detail in behavior. The fossil record also reflects where preservation could occur. Wetlands, floodplains, and shallow waters favored fossilization by burying remains quickly under fine sediment. Environments that lacked these conditions left fewer traces. Absence in stone does not always mean absence in life. It often signals landscapes where preservation was unlikely. The record becomes uneven, dense in some chapters and sparse in others. Despite these limits, fossils act as chemical snapshots. They capture bodies scaled to atmospheric conditions of their time, revealing what physics permitted under that specific balance of gases. When wings exceed modern proportions repeatedly across distant regions, the signal is consistent. It reflects environment rather than anomaly. These patterns allow reconstruction of broad constraints, even when individual stories remain incomplete. Much remains unknown. Fossils do not record color, sound, or interaction. They do not reveal how insects responded to daily variation or how flight felt within shifting air. They cannot show learning, choice, or nuance. What they offer instead is boundary. They show where life stood relative to what the planet allowed. In this way, insect fossils preserve more than anatomy. They record a moment when chemistry, physics, and biology aligned differently than they do now. Each wing pressed into stone is a measurement, not of motion, but of possibility. Images of this era often arrive already sharpened. Wings are enlarged into weapons. Mandibles stretch into threat. Movement becomes attack. In popular portrayals, scale is treated as intent, as though being large automatically implies violence. This framing borrows more from modern fears than from the world it claims to represent. Aggression is frequently exaggerated because it feels intuitive. Large animals today are often predators, and flight is commonly associated with pursuit. That expectation is projected backward, reshaping ancient insects into aerial hunters that stalked everything below. This narrative compresses complexity into spectacle. It replaces environmental context with confrontation, flattening a layered system into a single emotion. Danger is magnified in similar ways. Films and illustrations depict skies crowded with swarming giants, each one an immediate threat to anything that moves. The Carboniferous becomes a hostile landscape rather than a stable one. In reality, danger in that world was diffuse and quiet, distributed across moisture, fire, and terrain rather than concentrated in predators. Size alone did not generate peril. It reflected accommodation. The assumption that size equals threat emerges from modern ecosystems shaped by competition and scarcity. Today, large flying animals occupy niches where speed, vision, and interception matter. That was not the structure of this earlier sky. Without aerial rivals, large insects had little reason to evolve aggression or pursuit. Their scale served efficiency, not dominance. Flight favored endurance and stability rather than violence. Popular culture often removes these insects from their environment, isolating them against blank skies or modern backdrops. This separation strips away the conditions that explain their form. When placed against contemporary landscapes, their size appears unnatural. Within their own world, it was proportional. The forests were vast, the air was permissive. Space reduced conflict rather than amplifying it. Distortion also comes from framing this era as a brief anomaly or mistake. It is presented as a freak interval when nature briefly lost control before correcting itself. That view overlooks the slow processes that shaped it and the long duration over which it remained stable. Nothing about the Carboniferous was accidental. It followed physical rules applied under uncommon alignment, not narrative excess. Preserving wonder does not require exaggeration. The true story holds scale without menace and difference without threat. Giant insects are remarkable because they existed quietly within constraints that no longer align. Their significance lies in what they reveal about atmosphere, physics, and time, not in imagined hostility. When myths are stripped away, a calmer image remains, a sky that allowed size without conflict, bodies shaped by diffusion and lift rather than aggression. An era where growth unfolded without spectacle and receded without catastrophe. Accuracy does not diminish fascination, it refines it. By resisting distortion, the Carboniferous can be understood as it was, not as a monster filled prelude, but as a sustained moment when the planet briefly permitted more air, more space, and more patience. The wonder of that world does not come from fear, it comes from alignment, from a reminder that scale alone does not define danger, and that the most extraordinary chapters in Earth's history often unfolded without noise. Viewed as a whole, the Carboniferous reads less like an era of excess and more like a trial run. Earth adjusted a handful of variables and allowed the results to unfold without intervention. Atmosphere, climate, and surface processes aligned in a way that widened the range of what biology could express. The planet did not seek a particular outcome. It simply explored what followed from altered conditions. Within that widened range, life responded immediately and without reflection. Organisms did not grow larger because size was advantageous in any absolute sense. They expanded because chemistry and physics briefly permitted expansion. Diffusion reached farther. Combustion behaved differently. Forests accumulated mass instead of recycling it quickly. Each change opened space, and life filled it, not selectively, but completely. Biology followed opportunity rather than intention. This response was mechanical rather than purposeful. No lineage anticipated future constraints or preserved restraint for later stability. Growth proceeded until limits were encountered. When conditions shifted, forms that depended on those conditions receded. The process resembled an experiment in which variables were altered and outcomes recorded, not because the system sought knowledge, but because interaction produced results. The solutions that emerged were temporary by nature. Large insects, extensive wetlands, and high tolerance for fire functioned well within a narrow window. They did not generalize beyond it. These traits solved problems created by the moment itself, not by the long arc of planetary history. When the window narrowed, the solutions no longer fit. The system did not fail, it moved on. Throughout this phase, there was no foresight embedded anywhere in the system. Earth did not store memory of what worked. Life did not plan for reversal. Traits persisted only as long as they remained supported. The disappearance of large forms was not a correction or a lesson applied. It was a consequence of conditions, withdrawing support. Biology adjusted again, just as readily as it had expanded. This lack of planning is often misunderstood as inefficiency or waste. In reality, it is the defining feature of natural systems. Change proceeds without preference for permanence. What works now works because now exists. When now changes, outcomes change with it. The Carboniferous illustrates this clearly by allowing extremes to appear without ensuring their continuation. From a systems perspective, the era demonstrates sensitivity rather than stability. Small shifts in burial rates, atmospheric composition, or continental layout produced outsized biological effects. Life amplified chemical signals into visible form, translating invisible balances into wingspans and forests. When those signals weakened, amplification ceased. The system responded faithfully to inputs, not to narratives. Seen this way, the Carboniferous does not stand apart from other chapters of Earth's history. It follows the same rules, simply under rarer alignment. Earth tested biological limits by changing conditions, not by pushing life deliberately. Life answered by filling the space allowed, then withdrawing when space closed. What remains is not a story of excess undone, but of responsiveness revealed. The planet did not aim for giants, nor did it regret them. It permitted them briefly, as part of an ongoing process that explores possibility without attachment. In that sense, the Carboniferous was not an anomaly, but a clear expression of how Earth operates, testing boundaries, recording results, and continuing forward without pause. Coal begins as quiet accumulation. Within the dense forests of the Carboniferous, plant material fell into waterlogged ground and remained there, pressed flat by its own weight. Trunks, stems, and leaves settled into layers that resisted decay, not through preservation of form, but through persistence of substance. What remained was organic matter slowly compacted by time rather than recycled by life. As sediments built above these layers, pressure increased. Water was pushed out, chemical bonds tightened. Over millions of years, plant remains transformed into peat, then into denser material as burial continued. Heat from the earth below altered structure further, rearranging carbon into stable forms that could persist far longer than the forests themselves. Coal emerged not as a sudden product, but as the final state of prolonged patience. The thickness of coal seams reflects the scale of what preceded them. Carboniferous forests did not grow in brief pulses or narrow corridors. They spread across continents and endured for immense spans of time. Growth outpaced loss repeatedly, allowing organic material to stack layer upon layer without interruption. Where forests remained stable longest, coal seams grew deepest, recording not a single forest, but countless generations compressed into stone. These layers are unusual because few periods combined such extensive plant growth with such limited decay. In later eras, wood was broken down more efficiently, returning carbon to circulation before deep burial could occur. During the Carboniferous, conditions favored retention. Wet ground, resistant plant tissues, and slow decomposition worked together to preserve growth at planetary scale. Coal seams became the geological signature of that balance. Within each seam lies ancient sunlight. The energy captured by photosynthesis long ago remains stored in chemical bonds, sealed underground beyond reach of atmosphere and life. That energy traveled through time unchanged, waiting millions of years beneath shifting continents. Coal holds not only carbon, but history, compressed solar energy from a world that no longer exists. Rock layers surrounding coal preserve context as well. Alternating bands of shale, sandstone, and coal trace changing water levels, sediment flow, and forest expansion. Each transition marks an environmental shift, slow enough to sustain forests, fast enough to alter their fate. Together, these layers form a record written without intention, chronicling cycles of growth, burial, and transformation. Coal serves as a time capsule not because it was meant to be one, but because conditions allowed it. It preserves absence as much as presence, the absence of rapid decay, the absence of disturbance, the absence of return. Through this absence, deep time becomes tangible. Forests that once shaped air and sky are reduced to black seams that shape landscapes long after the air above them changed. When coal is exposed, cut, or examined, it offers a connection across eras, not through imagery or form, but through matter itself. It is the physical remainder of a world built slowly and dismantled just as patiently. In its density lies a reminder that Earth does not erase its past completely. It compresses it, stores it, and carries it forward, layer by layer, long after the forests have vanished and the sky above them has learned new rules. Later worlds carried the imprint of what came before, even as conditions settled into narrower ranges. After the Carboniferous passed, the atmosphere moved toward a steadier balance. Oxygen no longer fluctuated through extremes. It stabilized near levels that modern life would recognize, creating a consistent background against which evolution could proceed with fewer dramatic swings. This steadiness did not erase earlier influence. It transformed it into boundary. Within these boundaries, insects adjusted permanently. Smaller bodies became standard not because size lost value, but because reliability gained importance. Diffusion worked best within compact forms, allowing metabolism to remain efficient across a wide range of environments. Wings shortened and diversified, supporting quick movement, hovering, and bursts of speed rather than sustained gliding. Variety replaced magnitude. Insects spread into countless specialized roles, thriving through adaptability rather than scale. This shift reshaped the structure of ecosystems. With size constrained, competition intensified horizontally rather than vertically. Insects diversified into niches defined by diet, habitat, and behavior. The sky, no longer permissive of excess, favored forms that could react quickly and reproduce efficiently. Over time, these traits became deeply embedded, setting a pattern that persists today. Mammals emerged under the same atmospheric ceiling. Their evolution unfolded within a world where oxygen supported warm-blooded metabolism but did not allow bodies to grow casually enormous without cost. Energy demands remained high. Heat regulation required constant intake. Size increased slowly, tempered by the need to breathe, circulate oxygen, and manage waste efficiently. The planet rewarded balance over expansion. This constraint shaped mammalian traits from the start. Limbs evolved for endurance rather than sheer mass. Brains expanded carefully, supported by reliable oxygen delivery rather than abundance. Reproduction favored parental investment and efficiency over quantity. Mammals did not inherit a world of excess. They inherited one of limits that encouraged complexity within bounds. Plants also adapted to this more regulated environment. Decomposition became efficient. Nutrient cycles tightened. Carbon moved more freely between life and atmosphere. Forests persisted, but they no longer accumulated unchecked for millions of years. Landscapes became mosaics shaped by climate, geography, and disturbance rather than uniform expanses. Stability emerged from constraint rather than from permissive chemistry. Across all forms of life, the planet grew more selective. Conditions no longer allowed dramatic departures without consequence. Extreme traits faced immediate trade-offs. Survival depended on fitting within established parameters rather than stretching them. Evolution continued to innovate, but within a narrower corridor defined by consistent atmospheric chemistry. This did not make the world poorer, it made it denser. Diversity increased even as scale diminished. Life explored form, behavior, and interaction rather than sheer size. The memory of the Carboniferous remained encoded not in giants, but in the rules that followed them. A more constrained planet became a more intricate one. The legacy of giant insects lived on not through repetition, but through influence. Their existence demonstrated what was once possible, and their disappearance helped define what would follow. Later life evolved in their wake, shaped by a world that had tested abundance, recorded the outcome, and settled into limits that continue to guide life today. Balance reveals itself most clearly after abundance passes. The Carboniferous demonstrated this quietly, not through sudden collapse, but through gradual consequence. Conditions allowed extraordinary growth, and life responded fully. Forests spread without interruption, bodies expanded into newly opened space, systems grew dense and productive. Yet beneath that productivity, fragility accumulated in parallel. Abundance reduced margin. When growth proceeds without strong constraints, systems become tuned to narrow conditions. They perform exceptionally well within that window, but tolerate little deviation. The Carboniferous world functioned smoothly while chemistry, climate, and geography remained aligned. Once alignment weakened, even slightly, stress became visible. What had thrived through openness struggled when boundaries returned. Growth without limits did not fail immediately. It persisted long enough to appear stable. That stability, however, depended on continuation rather than adaptability. Large forms required permissive air. Vast wetlands required persistent moisture. Fire regimes relied on specific balances. None of these elements adjusted quickly. When change arrived, response lagged behind condition. The system did not break all at once. It thinned, fragmented, and simplified over extended time. From this sequence, restraint emerges as stabilizing rather than limiting. Later ecosystems operated under tighter constraints, yet endured far longer. Restricted oxygen levels, narrowed size range, but expanded resilience. Efficient decay prevented buildup but maintained circulation. Competition increased, yet adaptability improved. Stability arose not from excess, but from balance between input and removal. This pattern extends beyond any single group of organisms. It appears in nutrient cycles, climate regulation, and ecosystem structure. Systems function best when feedback limits extremes. The Carboniferous allowed feedback to weaken temporarily. The result was not catastrophe, but vulnerability that became evident only when conditions shifted. Deep time records these lessons without commentary. Rock layers preserve both abundance and its aftermath. Thick coal seams speak of growth sustained beyond balance. Fragmented forests and reduced forms speak of correction through constraint. Together, they show that success measured by expansion alone does not equate to endurance. Importantly, this lesson is not moral. Earth did not punish excess or reward restraint. The outcome followed physics and chemistry impartially. When conditions supported large bodies and extensive accumulation, those traits appeared. When conditions withdrew support, traits faded. The pattern repeats across eras, indifferent to scale or complexity. Balance, in this sense, is not an ideal state chosen by systems. It is an emergent property of constraints, acting consistently. When limits remain steady, life organizes within them efficiently. When limits loosen too far, organization becomes specialized and brittle. When limits tighten, organization simplifies and stabilizes. The Carboniferous teaches this without emphasis. Its story unfolds over millions of years, visible only in aggregate. No single moment signals transition. No dramatic event announces lesson learned. Instead, The message emerges gradually, written into atmosphere, rock, and lineage. In the long view, abundance is a condition, not a destination. Growth is a response, not a guarantee. Stability arises when systems remain flexible enough to absorb change without losing coherence. That understanding does not belong to one era alone. It echoes through deep time, carried forward quietly, guiding the shapes that life can sustain long after the forests of the Carboniferous have vanished, and the sky has settled into narrower rules. The strangeness of this world does not announce itself loudly. It emerges through absence. Familiar signals are missing, leaving space where expectation would normally rest. Landscapes feel full yet incomplete, occupied by life that follows rules, still recognizable but arranged in unfamiliar order. There are no flowers yet. Color does not rise from petals shaped for pollinators that have not evolved. Instead, green dominates in dense layers, broken occasionally by brown trunks and dark water. Reproduction relies on spores and simple dispersal rather than attraction. The land breathes quietly, driven by growth rather than display. Beauty exists, but it is structural rather than ornamental. The air carries no bird song. Wings pass overhead, but they do not sing. Sound is lower, softer, shaped by wind through foliage and water moving slowly through roots. Insects move with motion rather than voice. The sky is active without chorus. Silence becomes a feature, punctuated only by subtle mechanical noises, the brushing of wings, the shifting of leaves, the distant crackle of fire. Rhythms differ as well. Days feel heavy with moisture. Light filters through thick canopies rather than open crowns. Seasons pass without sharp edges, guided more by gradual change than abrupt transition. Growth does not pause dramatically. Decay does not hurry. Time feels stretched, measured in accumulation rather than turnover. Color follows chemistry rather than signaling. Without flowers or feathers, hues remain muted, greens deepen, browns enrich. Occasional flashes appear in the cuticle of wings or the sheen of wet surfaces, but these are incidental rather than intentional. Visual language has not yet diversified. Life communicates primarily through presence and proximity rather than contrast. Despite this unfamiliarity, much remains recognizable. Trees stand rooted, arthropods move along forest floors, amphibians slip between water and land, ecosystems function with balance and feedback, energy flows, matter cycles. The alien quality arises not from chaos, but from different priorities shaped by early conditions. Life operates under rules that feel adjacent to modern ones, not opposed. Gravity behaves the same. Water shapes landscapes. Sunlight drives growth. What differs is how fully these forces dominate without interruption from later innovations. No seeds yet wait dormant for opportunity. No feathers insulate warm bodies. No vocal displays fill the air. The system runs efficiently without them. This familiarity layered with difference creates a sense of dislocation. The world feels complete on its own terms, yet distant from modern experience. It resembles an earlier draft of a familiar story, coherent but unresolved. Many features that define later life have not appeared, leaving space where future complexity will eventually settle. The Carboniferous world feels alien because it reminds us that the present is not a template. It is a moment shaped by accumulated constraints. Earlier worlds were not incomplete versions of today. They were fully realized systems optimized for their own conditions. Standing within this imagined landscape, the feeling comes not from danger or spectacle, but from recognition without comfort. Life behaves logically, yet differently enough to unsettle expectation. It follows rules that still apply, just arranged before later layers arrived. The alien quality lies in that timing. Familiar life, living under unfamiliar rules, quietly reveals how contingent the present truly is. There was no moment when the giants vanished. No sharp boundary marked their passing. The sky did not empty itself in a single season, and the forests did not fall silent overnight. Instead, change arrived softly, almost politely, folding itself into ordinary time. Large insects did not disappear so much as recede. Each generation emerged slightly altered by conditions that no longer favored excess. Wings shortened, bodies lightened. What had once been effortless became costly, then impractical, then rare. The shift was gradual enough that no individual would have sensed it. Life continued exactly as before, only smaller, only quieter. Ecological replacement unfolded without urgency. New forms filled spaces left open by retreating ones, not as conquerors, but as occupants better matched to narrowing limits. The canopy still moved with wings, though they spanned less sky. The air remained active, though patterns simplified. Forest floors stayed busy with motion. Nothing stopped, nothing broke. This was not extinction in the dramatic sense. There were no final gatherings, no last survivors clinging to the edge of survival. The giants were not singled out or erased. They were gently outpaced by conditions that no longer supported them. The world did not reject them. It simply stopped making room. Life adjusted without ceremony. Nutrients still cycled, water still pooled and drained, fire still moved through vegetation when conditions allowed. The system retained continuity even as scale diminished. Change was absorbed rather than announced. The Carboniferous world did not collapse. It transitioned. Because the shift was slow, it left no witnesses. No creature marked the final passing of the largest wings. No memory recorded their absence. Each moment flowed seamlessly into the next, carrying only the present forward. When the giants were gone, there was no gap felt by the system. Something else had already taken their place. This quiet disappearance is easy to overlook because it lacks narrative shape. It does not fit stories of sudden loss or dramatic endings, yet it represents one of the most common ways life changes. Systems adjust incrementally until the past no longer exists within the present. Absence becomes normal without ever being named. Deep time favors this kind of change. It smooths transitions so thoroughly that causes and effects blur into one another. What remains is continuity, not disruption. The disappearance of giant insects followed this pattern perfectly. Their era ended not with an event, but with a drift. In this softness lies a particular truth. Not all endings are decisive. Many arrive as a thinning, a quiet narrowing of what is possible. Life continues, untroubled by what it no longer includes. The planet carries on without pause, indifferent to scale, attentive only to what fits now. The giants left no monument to their passing. Their legacy remains written into rock, chemistry, and constraint rather than story. They slipped from the sky without sound, replaced by forms better suited to the moment that followed. The change required no witness. It required only time. The sky above us carries memory, even when it appears unchanged. Its clarity, its limits, its silence are shaped by what no longer exists. The absence of giant wings is part of its structure, a condition inherited rather than chosen. Modern air reflects a history of narrowing, shaped by losses that unfolded too slowly to be seen. This world cannot return because the balance that allowed it has moved on. The atmosphere settled into steadier proportions, carbon cycles tightened, fire found new boundaries, forests learned to decay efficiently. Each shift closed a door that had once remained open. The Carboniferous sky depended on conditions aligning across land, chemistry, and time. Once that alignment faded, the sky followed it into the past. Planetary states are fleeting, not because they are unstable, but because they are transitional. Earth does not hold positions, it passes through them. Each state exists only long enough to express what conditions permit, then yields to the next arrangement. Giant insects belong to one such passage, sustained briefly by rare balance. Their disappearance marked not an ending, but a turning. Modern skies are shaped by ancient subtraction. What is missing defines what remains possible. Smaller wings navigate air that resists differently. Birds sing into space once shared with quieter forms. Insects hum close to the ground rather than gliding above canopies. None of this represents progress or decline. It reflects sequence. Sequence is Earth's dominant pattern. Continents drift, atmospheres adjust, life responds. No phase anticipates the next. Each unfolds fully, then recedes without regret. The Carboniferous did not prepare the sky for birds, just as birds did not erase what came before. Layers accumulate, replacing rather than correcting. This understanding shifts perspective. The Carboniferous sky was not a mistake that needed reversal. It was a moment when possibility expanded, then contracted as conditions evolved. That contraction shaped what followed by narrowing, rather than eliminating options. Complexity continued under constraint. Diversity flourished within bounds. The planet refined rather than repeated. Looking upward now, the absence of giants feels natural. The sky seems complete as it is. That sense of completion belongs only to the present moment. Another arrangement once felt equally whole. Future skies will feel the same to whatever life moves beneath them. Wholeness is temporary, defined by what fits at the time. Earth functions not as a destination reached, but as a sequence unfolding. Each chapter closes quietly, without declaration. The Carboniferous sky belongs fully to its era, just as the modern sky belongs to ours. Neither is permanent. Both are expressions of alignment, passing through time. The past sky does not linger as nostalgia or loss. It persists as structure, embedded in chemistry, rock, and inherited constraint. Its legacy lives in what cannot happen again as much as in what continues. When wings pass overhead now, smaller and faster, they trace paths shaped by absence. The ancient sky has folded itself into the present, not as memory, but as limit. In that way, the sky above us belongs equally to what is gone and what remains. It carries forward the quiet record of a world that existed once, briefly, completely, then yielded to the next chapter without resistance. Nothing about the Carboniferous was meant to last. It was a phase, not an exception, written in the margins of Earth's history. For a stretch of time, conditions aligned in a way that expanded what life could become. The planet explored that space fully, then allowed it to close. Seen from deep time, this sequence appears ordinary rather than strange. Life adapted without hesitation. When air grew permissive, bodies grew large. When limits returned, bodies followed them inward. Adaptation did not require struggle or intention. It unfolded automatically, shaped by chemistry, physics, and opportunity. Each form existed only as long as it fit the moment that held it. When the moment changed, form changed with it. The Carboniferous reveals that Earth does not aim for balance in advance. Balance emerges only after excess has passed. Systems overshoot, then settle. They expand, then contract. Through this motion, stability appears not as a fixed state, but as a moving boundary. Life continues by fitting itself to that boundary again and again. The planet carries no memory of prior arrangements. It does not preserve successful designs or regret discarded ones. Coal remains underground, fossils remain in stone, atmospheres adjust, continents drift. What persists is process rather than preference. Each era replaces the last without awareness of what came before. This lack of memory makes Earth resilient. Nothing is permanently favored. Nothing is permanently excluded. The Carboniferous sky gave way to narrower air. Narrower air made room for different solutions. Birds filled space once occupied by insects. Mammals followed under tighter constraints. Each wave arrived complete in its own context. The sky above us now is shaped by rules that once did not exist. Oxygen sits within narrow bounds. Fire behaves predictably. Diffusion limits size. These constraints feel natural only because they define the present. They are not universal truths. They are conditions inherited from sequence. Understanding this dissolves the idea of progress or regression. The planet does not improve itself, it changes. Each configuration expresses what is possible at that time and nothing more. The Carboniferous expressed abundance. Later eras expressed restraint. Neither state was more correct. Both were temporary. The giant insects belonged fully to their world. Their disappearance does not mark failure. It marks transition. The same will be true for every form that exists now. Life adapts within constraints until constraints shift. The planet moves on without pause. What remains constant is motion. Earth does not stay one way. It passes through arrangements the way weather passes through a landscape. The traces left behind allow reconstruction, but not return. Each sky exists only once. The Carboniferous sky no longer hangs above forests, yet its influence remains embedded in limits we now accept as fixed. Our world is shaped as much by what can no longer happen as by what does. That quiet inheritance is Earth's signature. A planet always in sequence, never finished, always unfolding into a new set of rules that, for a time, feel permanent until they too begin to change.